Here's the tutorial on how to properly make the figures for the current activity and also how to answer the questions. So let me demonstrate first with the mapping ocean currents. This is where we wanted to highlight the warm currents red, the cold currents blue. All of the equatorial currents, including the countercurrents, would be red. So even the south equatorial current would be red. Now, there is an additional current here you might want to add called the EAC. That would be red over in the South Pacific. In the North Pacific, the Kuroshio current would be red. When we go over to the Atlantic, we know that the North Equatorial current is red. The Gulf Stream is also red. That will be significant in a moment. And the Brazil current in the South Atlantic, that would be red as well. Over in the Indian Ocean, you have the South Equatorial current. We're going to color that red as well. Now all the others would be blue. The Oyashio current is a polar current, as is the Alaskan. The California current is bringing cold water along California. The Labrador current comes from the Arctic Ocean, so that's really cold. The North Atlantic, the Canary, we already talked about that one being a nice cold current in the Atlantic. In the southern hemisphere, the west wind drift basically is a current that goes around Antarctica, so it's all going to be cold. The Peru current will be cold. And the Benguela current over in the South Atlantic would be cold as well. So let's take a look at the questions we're supposed to answer. In what direction do gyres rotate in the northern hemisphere? Well, if you look, you can see that in general, they go clockwise. And that makes sense. So in the northern hemisphere, everything should go clockwise. The southern hemisphere, they tend to go counterclockwise. That's really seen in the South Atlantic. You can even see in the Indian Ocean. So we go counterclockwise in the southern hemisphere. What causes the rotation? Well, this is all due to the Coriolis force. What is the general rule for the presence of warm or cold currents along the eastern and western coastlines? Well, we can just focus on the east, or on the United States. On the east coast, notice we've got a warm Gulf Stream. On the west coast, you've got a cold California current. That holds true when we go down to South America. Brazil has the warm Brazil current on its east coast, whereas Peru has the cold Peruvian current. So east coasts are warm, west coasts are cold. What is the general rule regarding the temperature of currents moving toward and away from the equator? Well, if it's moving away from the equator, it's been heated by the sun, so it's warm. If it's moving towards the equator, it's bringing cold Arctic water down towards the equator, where it will be heated up by the Earth's, or by the sun's heat. Okay, that takes care of that section. I'm going to move on to the next section. All right, let's go ahead and make our graph here. I'm going to demonstrate real quick how it's done, and then I'm going to pause the video, finish it, and show you the finished product. So we're going to start with the 0 hour. Notice the wind is coming from the north at 4. So if it's coming from the north, that means the wind is heading south. Notice at hour 2, it's going south from the north at 10. So you're going to keep doing this. At 4 hours, it was from the north, heading south at 6. You'll have to excuse my arrows aren't very straight, but I'll do the best I can here. Okay, so I'm going to pause the video and I'll come back and show you exactly what it should look like when it's finished. Show you the finished. Okay, so this is the finished product here. This is what we're looking at. Let's talk about the questions that we had to answer to go along with it. The first question was, given the speed and direction of the winds for this period, predict when coastal upwelling was occurring. Well, in the reading, remember, we know that the strongest upwelling occurs when western coastlines in the northern hemisphere experience winds from the north. So when we have these strong winds here, whenever you see a nice strong wind coming from the north, you are seeing an upwelling event, because Ekman transport will force that water off the shore, and then therefore cold water comes up and replaces it. Well, that leads into the second question. If upwelling is occurring, will water along the shore be warmer or cooler? It'll be cooler because you have water coming from the deep ocean along the coastline. What do you predict about the productivity along the coast at this time? Well, so the water will be cold because it's coming from the bottom. Again, at these times, that's when we see upwelling occurring. Those upwelling currents will bring nutrients from the bottom, and that stimulates productivity. So we expect productivity to be high during these times because of the presence of nutrients. Now we're going to color our sea surface temperature graph. And what we're looking at here, the black represents the continent. Here's Vancouver Island in Canada, here's Washington, and then Oregon. These numbers are all sea surface temperatures. And we were asked to use a color code, with the warmest temperature being red. So notice 17 was the warmest color. So I'm going to color all the 17s red. All my 16s I would color orange, and so forth. So I'm going to go ahead and make this graph, finish it up, and then I'll show you exactly what the finished product will look like, and we'll talk about what we see. Okay, so here is what your finished product would look like, something like this. I might have made a few mistakes here. But the first question was, does this map show evidence of coastal upwelling? Well, yes, it does, because what we're seeing here is that the warm water has been pushed offshore, and you have this cold water here, all coming up along the coastline, replacing it. Where would you predict the highest amount per volume of water nutrients to be? Well, that would be where the blue is, because that's the water that is upwelling from the deep ocean. So remember, you're looking down on the ocean here from like a satellite view. So what you're seeing is the surface water is moving offshore. Underneath that, you have a deep, cold water welling up underneath. So imagine that dotted line there is the water from the deep ocean is coming up and replacing all of that water. So it's nice and cold. So that cold water would have the highest nutrients. And if this is the highest nutrients where you have the blue, that's also where you'd expect to see the highest amount of phytoplankton, because the nutrients would be fertilizer for the phytoplankton to grow. All right, now we're going to take a look at this last graph. And this graph is showing data from a cruise, a research cruise, off the coast of off the west coast of the United States. And so this graph, what we're looking at here, notice the vertical axis is water depth. So as you go down, water gets deeper. So that would mean the top of the graph represents the surface of the ocean. So I just draw waves there to kind of help me visualize what I'm looking at here. So everything here is the depths of the ocean. Now, when we say there's a cruise, we're saying a boat went out onto the ocean. So here's our boat, and it steamed out onto the ocean, and it stopped at 6 points. It stopped here, here. It's supposed to be a 3. Fourth one, fifth, and then finally at 600 kilometers it stopped there. Now each time it made a stop in the ocean, it sent a probe down into the deep ocean and measuring temperature. So all these numbers are temperatures. And as you would expect, as you go deeper into the ocean, it gets colder. what we're going to do now is we're going to make what are called isotherms, which are lines of constant temperature. And we're going to start with the 3 degree. So what you have to do at each station, you go down till you find 3 degrees and you put a dot. For the 5th one, notice there's no actual 3 degree measurement, but we know it has to be between these two, 2.85 and 3.46. So as you do that, you'll see a bit of a pattern. So I'm going to connect those lines. There's my 3 degree. So that takes care of that. I'm going to do a 4 degree now. So it's got to follow this pattern. We got to go up above 3.79 here, above 3.92, and over. So I'm going to connect those dots now. Didn't do a good job connecting those dots, but you can see the pattern. Now I'm going to go ahead and finish this up, and we'll talk about what it is we see here. Okay, so here is the finished product, and the only question we have to answer is, does this profile show evidence of coastal upwelling? Well, remember, coastal upwelling, or in coastal upwelling, we see cold water moving up towards the shoreline. And indeed, we certainly see that here. Take a look. This is all cold water going up towards the coastline. And when that happens, the cold water, of course, as it continues to go up, it forces warm water, such as this. Whoops. Let me erase that real quick. It forces warm water. This pocket of warm water has moved offshore. So this is a good example of coastal upwelling.